Hello students. So we'll start governors in this lecture. So you have seen the governor already, and you know its function also. So today we will study some of the governors, okay, and how to find how to relate the RPM with sleeve lift, okay, and the governors. Some mathematical derivations we will go through. So here you have seen that the function of a governor is to maintain the speed of an engine with within specific limits. Okay, that means a governor, when it rotates faster, the sleeve lift is higher, and then the your fuel flow will be higher. In that case, the engine, whenever it requires more amount of fuel, it will take it. Okay, and whenever engine speed is low, then the sleeve is also, sleeve lift is less, and there what happens, you don't have excess amount of fuel is not spent or not going through. It doesn't allow, the governor doesn't allow excess amount of fuel to go through. This is what you have seen in your practical, and you can see that you see, due to variation in the output torque of the engine, also we need a governor to maintain the speed. Okay, so now we have two types of governors: centrifugal and inertia. Centrifugal governors are those governors where we have primarily, basically, centrifugal forces. See, these are heavy balls, okay, and this is the sleeve. This part is called the sleeve, okay, sleeve. So when these balls, when the whole thing rotates, okay, so like this part rotates, okay, you have seen this, then the balls tend to move outward, okay, and because of that this part goes up, the spindle, okay, and whenever the speed reduces the RPM, then the balls will come closer to each other and the sleeve goes down. Okay, this is what you have seen already. Okay, now and you can see this sleeve is connected to this throttle valve. Here what happens, when this goes up, this opens, this throttle valve opens, and whatever fluid, it is fuel from here, it flows in a higher amount, and when it goes down, this gets closed a little bit, okay, and then the low amount of fluid is passing through, right. This part is, these two part are called arms of a governor, and this part is called a spindle. Okay, spindle. So you see, here we have pin joint, here we have pin joint, here also we have pin joint, spindle, and here also pin joints are there. So this can move, swing, these arms can swing like this. The spindle here, it has pin joint both sides, so spindle also can have some kind of relative motion like this. Now for centrifugal governors, the spindles do not have any role. Only the centrifugal force of these balls, okay, cause the sleeve lift. And when these balls additionally, centrifugal force is there, plus additionally this spindle is also rotating, right? These two spindles, because this part is rotating, means the spindles, these two spindles are also rotating, okay, and they will also cause some kind of centrifugal force. Because of these spindles also we have some, and this causes the sleeve to lift again, okay. So this, whenever spindle additionally causes some extra sleeve lift, I mean, ball is causing sleeve lift, that is okay. But additional sleeve lift because of the spindle movement, then we will call it as inertia governor. Okay. Otherwise, whenever there is no sleeve lift is because of only the balls, okay, centrifugal forces, then we call it as centrifugal governor. Okay. So to summarize, centrifugal governors, when only centrifugal forces are there for balls, that causes the sleeve lift, and in inertia governor, centrifugal force from the balls plus centrifugal force from the spindle. Okay, actually not centrifugal force exactly, but some force from this spindle causes the sleeve to lift up. Okay, now next you have a few some of the governors that is actually written the names: Watt, Porter, Powell, Hartnell, Pickering, spring control, cavity governor. These governors are different type of governors, and they have different uses, and their construction is from simple to complex. That type of construction is there. Okay, and we will actually go through two of them, Porter and Hartnell. Okay, so Porter governor is where we have a heavy mass here. Okay, here at the spindle part we have a heavy mass. Sorry, not spindle. These are the spindles. Sorry, this is spindle. This is arm. Okay, so at the sleeve part we have a mass M, heavy mass. This kind of mass is present. Okay, you can see if you search in internet. So there are two balls, and the balls are connected in this manner. So the balls have mass of small m, and this part is having a mass of capital M. Understood? Okay. Now what happens when it starts rotating? The balls will move apart. Okay. This is a type of centrifugal governor. Okay. So in this case, we will have centrifugal force of these balls. Okay. So the thing is, if this is radius r, okay, and the mass is m here, so the centrifugal force of this ball will be m r omega squared. R1 also will be m r omega squared. So we will have this m r omega square force. Its own weight is there, so that is mg. Okay, so the mg makes an angle with this your with this spindle and an extended portion of your arm. Okay, theta and beta, this angle will change. Okay, accordingly whenever we increase the speed, because if you increase the speed the ball will move farther like this, and then you can see that the angle theta gets increased, beta gets decreased. Okay, and when we reduce the speed this will be here. Okay, and you can see the beta gets increased, theta gets decreased. Okay, that happens. So these angles theta and beta, they are important. Also this length. Okay, c is the length from an imaginary point I. Okay, which actually this I we get by extending the arm. Okay, virtually extending it and virtually drawing a horizontal line from the sleeve position here. Okay, so this c is the distance from this point to the line of action of your weight of your balls. Okay, and b is further distance from the ball weight force to another force. Here we have another force here. This force is because of this heavy mass m. Okay, mg is there, its weight is there. So capital M is different, capital M and G. This is its weight is this m, capital mg, and the weight of the smaller one is small mg, small mg. So here you can see that we have written mg plus minus f, something like that. Now the thing is, mg is the total weight of this. Okay, fine. Now you see, sleeve if moves up. Okay, this sleeve suppose moves up. What happens? There is some slider. I mean, it has to slide through something. Okay, that will cause some friction. So when it moves up, friction will be downward. Okay, yes. And when you slow down, sleeves moves down. So there will be friction upward. Yes. Okay. So friction has a change in change in its sign. So we write plus minus friction. Okay, friction one direction we take it as plus, suppose upward one, and a negative downward one we take it as negative, suppose, because friction is changing, plus minus plus minus. Okay, so because of this sleeve. Now mg is downward always, so we take it as positive. If we take downward force as positive, then friction if becomes when it becomes downward, that will be positive, and when the slip moves up, friction will become negative. So we write mg plus minus friction. This is the total force acting at this sleeve. Okay, sleeve portion. Now by 2, because we have taken the half portion here. Okay, the another half portion is there, this side, this side. Okay, this side, that is not shown. We are calculating the half portion only, so that's why we have divided equally. This part, this half portion contributes to, I mean, takes into account, I mean, see, together these two balls are lifting this, right? So they will counter the total weight together. So half half equal, because their lengths are equal, masses are equal. Okay, so this will lift half of this force, and this will lift half. Together they will lift the total one. That's why mg plus minus f by 2 is there. Okay, so we have shown half portion, that's why this is half. Now you can please go through this. Capital M is the mass of sleeve, small m is the mass of each ball. This small f is force of friction at the sleeve, at this sleeve. Okay, so we have seen this thing. So this is written when it goes up down, just plus minus, so we write is plus minus, and by 2 is because we have to we have taken half of the portion. Now if you take the moment about this point, okay, then you can see that this force is causing a, what you see about I, this will cause a clockwise, sorry, anti-clockwise moment. Mr omega square will cause an anti-clockwise moment. Mg, this force will cause a clockwise moment about I. Okay, and then this mg plus minus f by 2 will also cause a clockwise moment about this. Okay, like this. Right, now we will write down this one, the moment. We take moment about I and we write this equation, mr omega square into the distance. So mr omega square into the distance, we have taken this as a, small a. Okay, so mr omega square a, this is what, anti-clockwise moment, which will write it in the left hand side, and all like moments, okay, unlike, so these are in the opposite direction, so we add them and write them in right hand side. Okay, so mr omega square, mr omega square a is there. So actually a is divided here, actually we have then skipped one line here. So here you see mg multiplied by c. Okay, so mg multiplied by c is there, plus this force multiplied by c plus b. So this whole thing mg plus minus f by 2 into c plus b. So mr omega square a was there, a we have taken here in this direction, c by a. So here c by a plus b by a. So this c by a and b by a, we trigonometrically can write something from here. You can see, where is it? See, c by a. Okay, if we take this angle theta, so this is perpendicular by base, that is tan of theta, and b by a, if we take, that will be tan of beta. Okay, so this is c by a, tan of theta, this is tan of beta. So c by a is tan of theta. We can also write it as r by h, because you see this is r and this is h. You see, because this theta and this theta are same. So r by h, p by the perpendicular by the base, this is r by h, so it is tan theta. And again tan beta, which one is beta here, we have to find it out. So here this angle will be beta. Okay, so here you can see beta is b by a. By the way, we kept it as it is, b by a tan beta. So we just write one more term, k, that is tan beta by tan theta, because we will actually divide it. You see, this one c by a is what, tan theta, this part is tan theta, this is tan beta. Okay, so tan beta, but we just divide everything by tan of theta. So this becomes 1, because c by a is tan theta, so we divide, or you can say like we divide the whole thing by c by a. So c by a gets cancelled out. This becomes c by a by, sorry, b by a by c by a. B by a is tan beta and c by a is tan theta. So this becomes tan theta by tan beta by tan theta. So this is actually k. We have taken this tan beta by tan theta as k. So we write it as here k. This is k. Okay, so this will become 1, and this will become 1. And because since we have divided by c by a or tan theta, we have to multiply with also c by tan theta. So tan theta, in place of tan theta, we write r by h here. Okay, so a little bit of rearrangement gives this expression. Okay, at the end, this is in place of, we have written omega as 2 pi n by 60, and we have derived this later on. Okay, when you calculate, we will get this thing, n square equal to 895 by h, this one. So here three things can take place. So three conditions. When k is 1, right, k will be 1 when these two angles are same. Okay, tan theta will be equal to tan beta, then that k will be 1. What happens here, you see, we put 1 here, 1, then this will be 2. So 2 2 2 2 gets cancelled out, so 895 by h. So this will be, instead of 2 mg, this will be mg plus mg plus minus f by mg. This is the case. Secondly, when there is no friction. Okay, when there is no friction but k is present, when there is no friction, this is 0, then what will have, 2 mg plus mg into 1 plus k. So sorry, g can be cancelled out here. G is common. So 2m plus mg into 1 plus k. Oh, sorry, g gets cancelled out. Capital M into 1 plus k divided by 2m. Okay, this is the expression. And when both are the case, when there is no friction and the angles are same, then this is simplified as this. Okay, just put k equal to 1 here and f equal to 0 here. Okay, then we'll have 895 by h into small m plus capital M by m. Small m is the mass of the balls. Okay, and capital M is the mass here. Okay, so let's go through some short numerical now. So in a Porter governor, each of the four arms is 400 mm long. So the length of arms are given. Okay, the upper arms are pivoted on the axis of sleeve, whereas the lower arms are attached to the sleeve at a distance of 45 mm from the axis of rotation. So let's construct this. So this is the upper arm. Okay, we call this as lower arm. Also we can call this a spindle. Okay, so upper arms are pivoted on the axis of the sleeve. So this is the axis of the sleeve. Okay, so this is pivoted. Here we have to pinch it. So its length is 400 given. Okay, and the lower arm here you can see, where is it, and the lower arms are attached to the sleeve at a distance of 45 mm. You can ask me why this is the case, because you have a bigger sleeve, kind of this kind of thing, right? So you cannot just attach it to the center. This has some diameter, isn't it? This kind of diameter is there. That's why we have to attach it here. Okay, so that is the reason we attach it away from the center line, so that portion, the distance is 45 mm from the axis of rotation. So this distance is also given 45 mm. Okay, so this is the axis of rotation, you all of you know. So this is the Porter governor, right? Porter governor. So we construct half of this diagram. This distance, you know, h, this distance is a. Okay, this is r. Remember this. This angle is here, this angle is theta, this angle is beta. Angles are important, we will have to use them. And this, you know, after construction, mr omega square will be the centrifugal force in this direction. Its weight is there, mg. And here you can see what is capital M g plus minus f by 2. Okay, so now let's further read the question what is given here. Okay, now each ball has a mass of 8 kg. So we know the value of small m, and load on the sleeve is 60 kg. So capital M value is also known. Okay, what will be the equilibrium speed for the extreme radii of 250 mm and 300 mm? That means at r equal to 250 mm, what will be the speed? Equilibrium speed means n. At r equal to 250 mm, what will be n? And again at 300 mm, what will be n? Okay, so that is the thing for two extreme radii. So 250 mm is the minimum radius here, and 300 mm will be the maximum radius here. That can go maximum, and 250 will be the minimum radius here. Okay, present. That means it can vary from 250 to 300. This much 50 mm it can go, this ball, right? So what will be the speed when it is at 250, and what will be the speed when it is at 300 mm r value? So here you have to neglect frictional forces. That means this is the condition where f is 0. So to take this, okay, so let's see, we don't know theta and beta. We'll see how can we find out them. So using the geometry here, this is 400, right? 400. Can you just relate them somehow? We'll just see. Okay, this is theta. H is unknown. So this M is 8, capital M is 60. Now see BZ. Just how when you draw it, mark these. So BZ is equal to 45, and AO is equal to, or OA equal to 400 millimeter. So here actually this is actually r by h. Tan theta means r by h. Okay, so we can also write tan theta. This is the equation, right? Mr omega square tan theta into this. This is the equation. This one. Okay, mr omega square r by h is nothing but tan theta, right? This is r by h tan theta, isn't it? So this we have written. Now f is not there, so f we can make 0. So here this will be mg plus mg by 2 into 1 plus k, right? So you have this r value at 250. You see, actually there are two cases. First thing is when this r is the minimum, that is 250. Okay, 250. This is the minimum value. And when r becomes 350, 300, 300, this sleeve will be the same, no, 400 only, 400. So in both cases, two different angles theta will have, isn't it? Here at when r is 250, we'll have some angle theta, and here also will at r equal to 300, we'll have some bigger angle theta, isn't it? This angle. So in both cases, we have to find out tan of theta. Then we can use the equation, because otherwise everything else is known. M is given, r is given, omega they are asking. Okay, theta you can find. Then here we can find out m is known, capital M is known, k can be known because tan theta by tan beta. If you can calculate tan theta, you can calculate tan beta also. Now, let's see that thing. So tan theta r by h, r is 250, 250. Okay, so this is 400, right? So let's find out this part. This part will be what? R square plus this is h square equal to 400. So we want to find out h square, right? So h square will equal to 400 minus r square. That is root of 400 minus r square, isn't it? So this one, root of 400 minus r square, or OA is 400, right? OA is 400. So h will be equal to, in this case, here you can see this h from trigonometry only. This is a from Pythagoras theorem. This 400 h will be equal to what? H will be equal to root of 400 square minus r square. Okay, that is what we have done here. So here you can see 400 square minus r is 250 for the first case. So we have taken it like this. R is 250, here we have taken. So tan theta we have got the value 0.8, right? And we need to get beta also. For that we need to find out this b. Okay. Now what is b? Just very carefully you can see this is r. This much is b, and plus additionally 45. If we add to b, we get a total length r. So r is equal to b plus 45, right? Yes. So we can find out b. So how do we find out b? R equal to b plus 45. So b equal to r minus 45. So 250 minus 45. So 250 minus 45. Okay. We got this. This is 205. Okay. Then we have the value of b also. What else we need? We need a. We can get this a also now. See, this is a, no? This much is a. So this is b, this is a. How do you find? You see, again from just a moment. We need some additional information in this case. Here you see a is equal to root over ab square plus. So here you can see ab. Where is ab? AB. This distance. Okay. This distance is again 400. By the way, see, we have 4 arms. This information is given. 4 arms. What are the 4 arms? Let's go back to the diagram. 1, 2, 3, 4. Okay, these are 4 arms. These are actually we call spindle, but for centrifugal governors, we don't have any. I mean, the spindles do not contribute to its sleeve lift. So all of them are arm. 1, 2, 3, 4 arms. So all the arm length is 400. 400. Our 4 arms is 400 mm. So that means we know the length of AB also 400. Now we need know the length of B also. So we can find out this length. Okay, small a, this part. So that is from Pythagoras theorem, root over AB square plus B square. Okay, we get this length. Fine. Now since we know these two lengths, we can find out beta, isn't it? B by A is tan of beta. So tan of beta is B by A. Yes, B by A. You can see this here. This is then beta, perpendicular B by base A. This is A. Perpendicular B by base A. Tan beta. So tan beta is B by A. B and A both lengths are known to us, isn't it? 205 by 2 and theta is known. So from here we can get K. So this was the only unknown here, right? Okay. So others, everything is known. So sorry, we need to find out omega. That is fine. Okay. So fine. Just put every value here. Okay. This is small m is the mass of the ball. Capital M is the mass on the sleeve. So here this mass was 60 kg. Okay. 9.8 1 by 2. So this we put here value of K. From here you get omega. Omega square is 237. Okay. Oh, sorry, I have made a mistake here actually. This part is omega square. Square. So you have to take the square root of this. Square root. So you have to take the square root and then solve. This answer may not be correct, but solve correctly. Okay. So 2 pi n by 60 is equal to root of 237. And then you have to get this value of n here. Okay. So similarly, just repeat the same thing when r is equal to 300. When r is equal to 300 mm. So here you see r is equal to 300 mm. So what you have to do, you have to find out tan theta. You find it out. You know how to find. Same process, just by putting, previously we have put 250, now we'll put 300. So when it is 300, when it is 300, r is 300, so this is 400 now. So you have to find out the angle theta. How do you find? You know, isn't it? This is 300, this is 400, so you can find theta. Again here, this is 45, obviously this r is now 300, and this part will be here. So beta also we need to find out in this case. Beta, how do you find that? You also know. So here this b will change. B, that will be 300 minus 45. So this b is known. A you can find out because this length is for 400. So everything you do, and you get the value of k for the second case when r is equal to 300. K will only change, that is 0.73. Other remaining, everything else will remain same. One more thing is tan theta also change. Okay, tan theta will be 1.1. So that you have to find out tan theta. Okay, so you put it, and next, I think this is correct, the previous one was wrong. So this omega square, whatever you get, then you take the square root, then you put in place of omega 2 pi n by 60, and you can get the split. So finally you can say that at n equal to 159 rpm, you will have the highest amount of sleeve lift. See, this is wrong. This answer is wrong because you have not taken the square root, because you see speed is more, so sleeve lift will also be more in this case. So but you can see radius is less. That means since radius is less, this is not correct. This will be less. Okay, I made a mistake in this calculation, but I think this is correct. Okay, so you do the calculation yourself. Okay, we'll stop here and we'll continue our discussion in the next coming numericals. Thank you.